Now we're going to go into more detail with horizontal and vertical components. It says the horizontal and vertical components, respectively, of a vector u having a certain magnitude and direction angle theta are given by the following. A, which is the horizontal component, is equal to the magnitude of the vector times the cosine of the direction angle, and B, the vertical component, is equal to the magnitude of the vector times the sine of the direction angle. So I want to show you to make sure you understand why these formulas are what they are. Okay, so I drew a little sketch on page 1, but I think I wrote too much on it, so I'm going to just draw a fresh sketch on this page. So here we go. We are dealing with a vector here. All we know about the vector is its magnitude and its direction angle. Okay, we are told that is what's going to be given. Okay, so we are going to break this thing down into components, okay, and explore the components more. So anytime a vector has components, that means it's a position vector. So you are going to have to put it somewhere in the plane. Okay, so I'm drawing my x and y axes here, and I'm just going to keep the sketch pretty identical to what I had on the first page. So here's my y-axis, here's my x-axis, and then I drew a vector that was in quadrant 1. And so since it's a position vector, the initial point of the vector has to be the origin, and then we're just going to say the terminal point is some generic point AB. Okay, so this point right here is the terminal point. It has coordinates AB in the coordinate plane. Okay, so here's what we have. Like I said, we're going to be given, the only information we're going to be given about this vector is its magnitude. It has some magnitude, okay? That's the length of this red vector. And then the other thing we know is the direction angle is theta. Remember, the direction angle is going to be the positive angle that is formed by starting at the positive x-axis and rotating to the vector. Okay, so this would be the direction angle. Okay, so again, these are the two pieces of information that if you are given, you can figure out both the horizontal component and the vertical component of the vector. Okay, so here's how. Let's break this thing down into components. Okay, so what you would do here is you would draw from your terminal point, draw down to the x-axis, and that creates this right triangle. Okay, so when we look at this, okay, this is going to be the horizontal component, and this is going to be the vertical component. And what we can do here, okay, if again I gave you this, idea back on the first page. If you start at the origin, the horizontal component and the vertical component, they tell you how to get to the terminal point. Okay, so if you start at the origin, you would have to walk in the x direction. You'd have to walk in the x direction to the right here by a many units, okay, because this point has an x coordinate of a, so that means this distance right here is a units, okay? And then once you get here, you have to go up b units. So this distance right here is b units. Okay, so the vertical component is b. Okay, so that terminal point is really telling you the components of your vector. The horizontal component, we're calling it a, and then the vertical component is b. Okay, but how do you actually calculate their value? Okay, you can do so if you are given the magnitude and the direction angle. Okay, so because we have a right triangle, we can apply some right triangle trigonometry here. If we go across from the right angle, we see that the magnitude, the length of the vector, that is the length of the hypotenuse, okay, for this triangle. Relative to the direction angle, if we go across from the direction angle, this is going to be the opposite side, and then that makes the other side of the right triangle the adjacent side, okay? So looking at it from that perspective, we can solve for the components. Okay, so say we wanted to solve for A first, the horizontal component. Okay, so side A over here, that's going to involve the adjacent side, and I'm going to use the hypotenuse as well because the magnitude would be given to us. Okay, so adjacent over hypotenuse, that is cosine. Okay, so the cosine of theta is equal to the adjacent side, which is A, over the hypotenuse, which has length, the magnitude of vector u. Okay, so like I said, we'd be given the direction angle, so we could plug in for theta, so we could compute the cosine of theta, and we'd also know the magnitude of u, so this denominator would just be some number, so we could solve for the unknown, which is A, the horizontal component. Okay, all I have to do is multiply both sides of the equation by the magnitude, okay, and that's going to tell us that the horizontal component A, you can get that by taking the magnitude of the vector and multiplying it by the cosine of the direction angle. Okay, you can do the same thing for the vertical component. Okay, if you look at B and you're trying to calculate the value of B, we know B is the opposite side of this right triangle, so we can do opposite over hypotenuse. That's sine. The sine of the direction angle is going to be B, the opposite side, over the hypotenuse, which has length magnitude of the vector. Okay, if we multiply both sides by the magnitude, this is going to tell us that the vertical component is going to be the magnitude of the vector times the sine of the direction angle. Okay, these two formulas right here, that's what is being said right here. Okay, they match. Okay, so what this box is telling you is how to compute your horizontal and vertical components of your vector given the magnitude of the vector and the direction angle. Okay, if you read the last statement in the box, this gives you another way of writing your vector. If you have vector u that has a horizontal component of A and a vertical component of B, you can write it this way. You can rewrite the horizontal component as the magnitude of the vector times the cosine of the direction angle, and you can write the vertical component as the magnitude of the vector times the sine of the direction angle. Okay, so let's get some practice doing this, okay, where we break our vector up into horizontal and vertical components. In example 2, it says vector v has the given direction angle and magnitude. Find its horizontal and vertical components. So we are told that the direction angle is 146.3 degrees and the magnitude of the vector is 238. Okay, so this vector has components, which means it's a position vector. So we need to draw the xy plane. Okay, so here's my x-axis. And then let me put in the y-axis. Okay, so it looks like this. And I'm not going to put a scale on here, okay? So what is really going to matter here is the direction angle, okay? We need to eyeball it. It's 146.3 degrees. So remember, to draw a direction angle, it has to be positive. You need to align yourself with the positive x-axis and rotate counterclockwise through an amount of 146.3 degrees, okay? So just eyeballing it, so say it's maybe about right here, okay? So here's the vector, here's the terminal point, which is the origin, or sorry, here's the initial point, which is the origin. This is the terminal point, okay? We don't have a scale on here. What I can label on here is that this is the direction angle. Okay, if I rotate from the positive x-axis to the vector itself, this is 146.3 degrees. This is the theta value, okay? I don't know the scale, like I said, but I know the length of this vector is 238, so I can just write it on there, okay? All right, so what we want to do is break this thing into components, okay? So if you take the terminal point and you draw straight down to the x-axis here and form a right triangle, okay, this is going to be the horizontal component A, and this is going to be the vertical component B. Okay, so the terminal point, it has coordinates A, B. Okay, we're just trying to figure out what the A and the B are. Okay, so what you can do is use these formulas that we just derived. Okay, so if you want the horizontal component, that's going to be the magnitude of your vector times the sine of the direction angle. And if you want the vertical component, that's going to be the magnitude of the vector times the, oops, I wrote the wrong thing. The first one, the horizontal component, should be the magnitude of the vector times the cosine of the angle. And the vertical component should be the magnitude times the sine of the angle. Okay, so that's what we need to do here. Okay, so let's find the horizontal component first. All right, so to do this, the A value is going to be the magnitude, here it's vector V, times the cosine of theta. So this is going to be the magnitude of the vector is 238. We need to multiply that by the cosine of the direction angle, which is 146.3 degrees. So let's pop this into a calculator. So we've got 238 times the cosine of 146.3 degrees. Make sure you're in degree mode. And then here is the component. Okay, so I'm just going to write this out. So negative 198.005. I'll write the rest of this, okay? All right, so that is the horizontal component, okay? That means if you start, if you're measuring from the origin here, this yellow distance right here along the x-axis, that is going to be this number, negative 198.0050811. Okay, it definitely makes sense to have a negative horizontal component. If you had done this, if you had done the calculation and you got a positive number, something's wrong. Okay, because based on the picture, the horizontal component should be negative. Okay, the vertical component, when we compute it, because the vertical component, we're above the x-axis here, it should be positive. Okay, so let's do the same thing to get the vertical component. So here the B value is going to be the magnitude of vector V times the sine of the angle. So this is going to be 238 times the sine of 146.3 degrees. Okay, so let's see what we get this time. Okay, so here it comes. Here's the answer. So 132, it's positive, yay. And I'll write the decimal expansion. Oops. All right, so here we go. Okay, and you know, this makes sense. We got a positive number. Okay, so this blue distance right here, okay, that distance is going to be 132.0529 and so on. Okay, this is the yellow distance. Okay, so we've broken our vector up into its horizontal and vertical components. Okay, so what that tells us is the point in the plane, the terminal point, okay, I'll write it over here. The terminal point of this vector is located at this point, AB. Okay, so the A value is this negative 198.005. I'll just round to 4 places after the decimal. The vertical component is this point, or is this number. Okay, so that's this terminal point. Okay, we know the horizontal component, which is the x value, and we know the vertical component, which is like the y value. Okay, that is what this is telling us. Okay, you may be wondering, okay, can I draw the picture and look at this thing and use the right triangle to figure out the components? Okay, so let's talk about that before we move on. Okay, this is the answer. We're done with the problem, but I want to address the issue. Can I use the right triangle to do this? Okay, if you look at the right triangle that I've drawn, theta is not inside the triangle. Okay, what you have is this angle alpha, and alpha plus theta should give you 180 degrees. Okay, so alpha plus theta should be 180 degrees. So if I'm trying to figure out the angle inside the right triangle, it is 180 degrees minus the theta value, which is 146.3 degrees. Okay, so let me go figure out what that is. Okay, because I think it's important to see this. If you do 180 degrees minus 146.3 degrees, that's going to give you an alpha value of 33.7 degrees. Okay, so if I looked at this, okay, I could say, hey, the cosine of alpha, that's going to be opposite over hypotenuse, so that's going to be A over the magnitude of the vector here. Okay, so this is going to tell me the cosine of 33.7 degrees is equal to the A value over the magnitude, which is 238. So this is telling me that A is 238 times the cosine of 33.7. Okay, so I'm just using the information from inside the right triangle. If I went this route, look what happens. You do 238 times the cosine of 33.7. It's going to give you a positive horizontal component. It gives you the same number. Okay, if you look up here where my arrow is, it gives you the same exact decimal expansion, but it gives you the wrong sign. So you could do it with the reference angle alpha, but you have to be cognizant of signs. Okay, so like if this popped out of your calculator, you would have to make this value negative because the vector's terminal point is in quadrant 2. Okay, if we did this and we tried to compute the vertical component, so you would instead do the sine value, okay, it's going to come out correct. Okay, but the moral of the story here is if you are trying to compute your components, okay, you can use it's best to just use these formulas with your direction angle. Okay, if you use the direction angle, it's going to output the correct sign. Okay, if you don't want to memorize those formulas, that's fine. Just draw out the right triangle. But when you use the reference angle alpha instead of the direction angle theta, you do have to adjust the signs for the quadrant. Okay, so just keep that in mind.